Hello, everyone, and welcome to the show. This is the Geek Narrator podcast, and I am your host, Kaivalya Apte. Today, I'm back with another episode which is focused on databases. And today's database is pretty special. It's pretty new when we talk about other databases. And to talk to me about the database, which is DuckDB, we have the CTO of DuckDB Labs, Mark. Mark, thanks a lot for joining us today. I'm really excited to have you. And I am really excited to go deep into DuckDB and understand how everything works. Why don't you start with a little bit of introduction for our viewers about yourself, about a little bit about what you're doing at DuckDB?
Yeah, absolutely. I can. I'll just start with a short introduction of myself. Hey, my name's Mark. I like databases. That's usually how I introduce myself at parties. It's a big hit, as you might imagine. So what got me here is essentially like, when I did my master's in computer science, I went to a research group at the CTO, the database architectures group, where they basically built databases. Like that was their expertise there. Mm-hmm. And so I got in there and started working on database engineering, right? Like the construction of database systems. And also we had some collaborations with data scientists and data analysts there. And essentially we were building databases. Like my master's and later on my PhD was focused on building database systems that were suitable for data analytics, data science, and getting data analysts, data scientists to use database systems. And what we noticed was that a lot of the people there either didn't use database systems at all, like they would just have a bunch of CSV files on a storage system, like sometimes terabytes of these things, right? Like it's unwieldy. And they would just load it with they would use bash scripts. They would use pandas, R was a big thing back then as well. Yeah. Still is, of course, but back then was a fierce battle between the two. And just scripting around these files, and they would avoid using database systems entirely. And I was working together with what's now my co-founder of DuckDB Labs, the company, and co-creator of DuckDB, the database system. And we're trying to get those people to use database systems because that's what our whole field was about, right? It's the research we were doing that we spent personally almost 10 years doing. We're thinking to ourselves, it's a shame that these people that are interacting with data so much, the word data is in their profession and it's the first word, right? Yeah. They're data engineers, data scientists, data analysts. And for them not to use database or to dislike using database, which we saw, we felt bad about that. We were like, how could this be, right? Because in our eyes, databases amazing tools, right? Yeah. They have been around for so long, right? The first databases come from the 70s, right? In terms of computer science, that's ancient history, right? That's a really long time they've been around. And they are super versatile, super well optimized, studied. People have spent their entire life on making these things as great as possible. For us, it was always a bit a shame. Hey, you have this great technology of database systems. Why are the data scientists not using them? Right. That's what led us to the creation of DuckDB, and how I personally got in that position. We tried a lot of other things as well before we did DuckDB, right? We tried to adopt existing systems to the solution to try to make them nicer to use, right? So we did a lot of work on user-defined functions, optimizing the client protocols. You can look at my website for some of our earlier works pre-DuckDB. Yeah. But in the end, the conclusion we reached was that there is just no system that fills this gap, right? There's no system that exists that fills this use case, which is why people aren't using database systems, but other things, because there's no database system out there that actually supports this use case in a good way.
Yeah, that does make sense. And that also gives a little bit of the problem statement, why DuckDB was created. And so as you mentioned, data scientists, they work with a lot of data, but there are different ways. There's no standard way of working with data and doing aggregations and analytics on top of it. And every data scientist use different tools, as you mentioned. So that was clearly a problem. And so what was the friction in using the existing databases? What was the primary reason data scientists were not able to use the existing solutions? Let's say like a full-blown RDBMS, for example, Postgres, or something like SQLite, or any client library or library like Pandas. What was the main problem there?
The reason there's actually like various reasons, right? It's not just one killer reason there, but a lot of the reason is around like integration with tools that they want to use, right? So databases are great, and SQL is an amazing language, right? Like SQL, you can do tons of great stuff in SQL.
Yeah.
But data scientists, data analysts, they often need that little bit extra, right? If you're running a machine learning pipeline, for example, or a classification pipeline, yes, there are some paths to implementing like support vector machines in SQL, but it's not a nice experience, right? If you want to run a neural network, or like you want to do KNN or something like that, right? You generally want to use a library. And it just so happens that most of those libraries, they exist in languages like Python and R. Originally R, and then now Python is, of course, I would say the leader in this domain. And they have a ecosystem there that is just unbeatable for that, right? There are like, some people have tried to push this into the database system, right? But it essentially always ends up with like many different problems. Like usually, if you implement this natively in a database system, then you're never going to be able to keep up, because you as like a database vendor, right? You're one company generally. The people that are working on these tools, right? Scikit-learn, TensorFlow, PyTorch, there's so many of them, and they're always coming up with new stuff. And of course, the people that are working in that domain, right? The data scientists, data analysts, they want to use the latest of the latest because it's usually the best, right?
Yeah.
So they are in this world of Python or R, right? They are in this domain because they need to be, because that's where all their tooling is. There's where all the package ecosystem is.
Okay.
And then if you then want to combine that, which is like I just said, basically a must, like you have to be in that ecosystem, then combining that with existing database is generally always quite painful. So if you take Postgres, for example, yes, it's one of the easier database systems to set up as far as client-server databases go, but it's still painful, right? Like you need to set up a server, you need to initialize the database, specify a catalog, you need to deal with like processes that are running, that are connecting to, and then you need to install a connector library, right? Like there's a lot of pain involved.
Yeah.
And the data scientists, analysts, they're also working with large amounts of data. And they need to push that data, not just inside the database, but they need to get it out again. So they need to extract the data back into Python, right? Yeah. Because they have to push it into their classification algorithm or their machine learning model. And that's essentially just always a giant bottleneck, because the traditional database systems, they're not built for that. If you think, what is Postgres built around, right? It's point queries. It's a transactional database. It's, hey, give me one row, give me 10 rows, right? It's never, hey, give me 100 million rows. Like that's not a normal Postgres query.
Yeah.
But even analytical databases aren't built for that, because what are analytical databases built for? They're built for, give me the result of an aggregate.
Yes.
And even though they may be optimized for processing many rows, they aren't optimized for exporting the rows and getting them into the Python process or the R process to then hand them over to another library, another module. So I think like the challenge with setting up the database server, like just the pain points there, together with the data transfer cost, like the data ingestion is usually slow, the data transfer the other way around is also usually slow, basically makes it so that working with these traditional database systems is a big pain, which basically means people don't want to do it, right? I think SQLite, actually, it's good that you mentioned that. I think SQLite is to some extent an exception, and also where we took a bunch of inspiration for DuckDB, right? One of the earlier taglines we had for DuckDB was that it's the SQLite for analytics. And one of the things that both SQLite and DuckDB share is that they are not client-server databases, right? Postgres and essentially almost every other database is a client-server database, which means you run a server as a separate process, and your application, Python, whatever, can connect to it using a socket connection. And that's problematic for this use case for, well, various reasons. the data transfer one is a big one, right? So because if your data lives in a separate process, you need to push that over a socket, which essentially means making a copy, but it's actually much more expensive than making just a copy. So there's a big cost to pay. If your data lives in the same application, which is the case when you use DuckDB and when you use SQLite, you can just interchange that data. You can just use it as is, which means that it's essentially extremely cheap or even free to move the data to and from the database, which makes it much more suitable for these kind of workflows because you can very easily extract 100 million rows from DuckDB into Python. Whereas if you want to do it in Postgres, it may take you like an hour or something, right? It's going to take you a very long time. And the other thing that's we noticed actually is very important is the if you think about like how people use Python and Python scripts and such, they are copy pasting around code. And that's not like in a bad way necessarily, right? You have a snippet of code that you share with a coworker that's, hey, this snippet of code imports data, it runs the scripts, right? Or you have these notebooks, right? Like you have IPython, Jupyter notebooks, people run code there. And generally people really want that code to be standalone. They want that code to be like, hey, this code downloads a thing, this sets up does the data processing, etc. And when you have a client-server database, you have external states, namely the database server. And if you think about like Postgres, how do you launch a database server? Well, you can't launch it from within Python. You need to launch like a bash script. So it doesn't really work with this model that people want to use, right? So this is a number of pain points. So SQLite actually solves that to some extent, which is what I started talking about here. Because it is this library, right? It's very easy to use. You just import SQLite and it's in the same process. But SQLite has one big problem. It has a few problems, but one big problem for analytics, which that it's a transactional system, right? It's built for point lookups. It's built for point queries. It's built for point inserts. It's not built for bulk ingestion. It's not built for fast processing of analytical queries. And it's just not very fast at that because it's not made for that, right? It's not a design flaw of SQLite. It's a design choice. And for its use case, it's extremely valuable. But for analytics, it's not good, right? It's not made for it. It always runs queries on a single thread, which is nowadays for analytical queries just a no-go, right? Like you can have it, if you have a machine with 48 cores or something, which is very possible, or 64 cores, running single-threaded versus running with 64 cores, it means a query that completes in 1 minute on 64 cores takes more than an hour on one core, right? Like the differences nowadays are crazy. If you process large amount of data, you need multi-threading, and it doesn't have that because it's not built for these kind of queries, right? So I think that's one of the big things. It's just not made for these kind of large data sets and the workloads that are associated with them. And that's why one of the reasons that we built DuckDB while still learning from the lessons of, hey, it's a library, you can import it, it's easy to install, it's very easy to set up, right? And that was always one of our goals as well.
Yeah, that makes a ton of sense. And I've used a few of those libraries and I can imagine the pain of data scientists, how it would be. You mentioned a couple of very interesting points, like one about SQLite, that it is a transactional database, so OLT style workloads. And then you also mentioned about the analytical databases that exist at the moment. Looks like there was no database which was like SQLite, but for analytics. So let's try to define. So I want to go a little bit more on the use case side, but we'll cover that later. And I'm more curious to understand how this has been done in DuckDB. So let's define what is DuckDB, just to understand, like, is it an analytical database? Is it both like transactional and analytical?
Yeah, like I said, we can go back to our old tagline. It's a SQLite for analytics, right? So it is an analytical database system. That is by far its main focus.
Yeah.
We don't do too badly on transactions. It's not something that we completely sacrificed either.
Yeah.
And DuckDB does have support for assets, right? Like it's an asset system. It does support all of the usual things you would expect from a SQL database system, right? Like you can insert rows, you can delete rows, you can update rows, you can do all the DDL, you can do schema changes, you can alter tables, add columns, all that stuff. Everything is isolated. There's transaction isolation, changes to the database. They're all like all atomic, like it's all or nothing semantics, like all of that stuff is supported. and it's not that bad at it. You can run a few thousand transactions per second in DuckDB, but the main use case is absolutely analytics, right?
Okay.
So that's what the system is the best at, is analytics. So would you like me to go a bit more in depth on what that means from the internals perspective, or what it means from like a user perspective?
I would say from the user perspective for now. We'll go into the internals in a bit.
Perfect. So what that means from the user perspective is that if you run a query in DuckDB that's like an aggregates query or a join query that involves like large tables, the system will be very fast at it, right? So the system does automatic parallelization of queries, which means that if you run one query that involves a large table, then the table will be partitioned. Each thread will operate on different partitions of the table, which will allow it to process very fast. It's also really optimized for this bulk processing, right? So that's what it's good at. Like you can, like full table scans is like the default mode of DuckDB. So whereas in a system like Postgres, right? If you run a full table scan, it's going to take you a while. In DuckDB, it's going to be very fast because that's what we have optimized it for. So it's all about like cache locality, like memory locality, like all about making sure that the table scans are as fast as possible. It's a columnar engine, like column storage. I think we'll get more into that later. But that also enhances the analytics experience because it means that even if you have a large data set, often you can prune a lot of it away, which means that the actual data you need to process because of these design decisions are a lot less. It also does a lot of compression, so it keeps data compressed in memory, which again reduces data set size. And all these design decisions basically lean towards trying to make the system process large-scale queries as fast as possible.
Makes sense. And given we've also talked a little bit about the existing analytical systems, right? So, for example, if I have to compare DuckDB with something like Apache Pinot or Druid, for example, so these are like real-time analytical databases, but it's like a separate cluster of database, right? And the client itself is running separately. What is the difference? Is it just that DuckDB runs on the same process as the client, or there is more to it?
So I think one of the differences that a lot of analytical databases that are out there open source are not actually using quite the state-of-the-art techniques. So they are probably pretty good, like at analytics, but there can still be like a lot of gains have been made as well in the last 10, 15 years. And DuckDB was designed with the latest of the latest in all these techniques, right? So we come from a background as database researchers. We have a lot of like contacts there. We talk to everyone essentially that has been working on these techniques, right? And we have implemented a lot of that in DuckDB. So in general, DuckDB is on the faster side, even for an analytical database system, right? Regardless of where it runs. But indeed, where you'll see like the giant speedups is in terms of this like data transfer, data interchange stuff, right? Because if you run we may be like 10x faster than Druid or something. I don't know, like just randomly shouting out a number, right? Or maybe 3x faster. I have not benchmarked that at all, right? Like just randomly shouting out a number. But where you're going to see like the 100x or the 1000x, right? Like the big gains, it's going to be in the data transfer, right? If you want to ingest data from DuckDB, it's Python to DuckDB. DuckDB runs right alongside your application. So there's no round trips to be made. There's no data to be pushed over a socket. Like it's all right there. And that means we can, the library becomes super flexible because you don't need to worry about these round trips anymore. And you can do stuff like, hey, I know how to do this in DuckDB. Let me just quickly go into DuckDB, go back to Pandas, or let me just quickly run a filter. Let me read a file. You can use DuckDB in a very versatile manner. And because it's designed to be this like in-process embedded system, right? The footprint is also very small, which means you can also bundle it with your application. And a lot of people do, right? People run them on these Lambda functions, right? Because it's such a small footprint, you can just plop it anywhere, right? And one cool thing there is that we actually have a WebAssembly version as well. If you go to our website, there's a WASM version, which means you can run DuckDB in a browser as well, right? So you can run DuckDB there as part of your website. And some people have built products around this as well, where they use DuckDB to read import files, stuff like that in the browser, right?
I'm more curious now to understand how things work. just a little bit more on how things are deployed. So let's say I have an application and I want to do a ton of analytics on, let's say, 100 gigs of data or something like that. How would the deployment model looks like? So is it always bundled with application, or does it run on the same machine but as a sidecar, or how does that work?
So I think that's something that's different from DuckDB and other database systems, is that you need to do that, right?
Okay.
So you choose as the application developer. So some people bundle it as part of their application layer. Some people have like dedicated boxes that just run DuckDB, right, as well. That happens. Some people launch like Lambdas to run DuckDB. We don't really do that for you. DuckDB is more, in that sense, a component that you can put in different locations, right? And I think that's also the strength, because you can put DuckDB anywhere and run in any configuration that you want. You're in control of that, right? We don't make that decision for you, where you have to say, okay, you have to deploy it in this way. We don't make that decision for you. We give you that decision.
Okay.
And in some sense also empowers quite unique use cases that we see.
Is it like a distributed database where, let's say I have 10 nodes of my application and I have DuckDB running as part of my application in an embedded manner? Is it still there some synchronization between the different instances I'm running, or each DuckDB process is a separate process and works separately on each data?
So there's no synchronization that we do.
Yeah.
But there are actually people that use DuckDB as a component in a distributed database system. So essentially, you can use DuckDB in multiple locations, right? In many different locations.
Yeah.
Because it's like, you can put it anywhere, right? It's very flexible in that regard.
Yeah.
But we don't do this communication at all, right? DuckDB does what you tell it to do, and we don't have any support for distributed computing or like launching processes or anything of that. It doesn't happen.
Okay.
Nevertheless, people do use DuckDB in that manner, often as part of their own application that may be distributed, where they just launch different DuckDB instances. What often happens is that if they have data that's stored in some data lake, like S3 or something, and it's read-only, which often happens as well in these use cases, or the data gets pushed by some other process, people fire off multiple read queries from different nodes on different machines, and there's no real coordination necessary often, because the system is fast enough to process until like hundreds of gigabytes of data on just one computer or one node, right? Like we don't do any sort of sharding, repartitioning. And in a lot of ways, it's also a simplifying factor, because you don't need to care about that. You just, you run the query and it works.
Yeah, fair enough. With this, let's start with the ingestion part. Let's say, since you also mentioned S3, like I have a ton of data in S3, for example, and I want to start using DuckDB. How would I ingest data?
So you can just read the data from S3, just query it directly.
Okay.
So one of the things that we tried to do with DuckDB is that we have our own storage format, which I think we're going to talk about more later, which has MVCC and everything. But we're super flexible about where we can ingest data from. And we also tried to treat that as a first-class citizen. So a lot of databases have a concept of like foreign tables. DuckDB doesn't have a concept of foreign tables. It just has the concept of tables. But we support tables from different sources.
Okay.
And one of the things that has always been important to us is that's like as powerful as anything else, right? So we can read data from Parquet files in S3, from CSV files in S3, from local Parquet files, local CSV files, JSON files. We can read data from SQLite database, from Postgres databases, soon MySQL database as well. And it's all transparent. And also, what's also cool for people that are using like Python and stuff, we can query like Pandas data frames directly, or arrow tables, right? Because it's all in memory in the same application. We can just say, hey, you have a SQL query of Pandas data frame, run it on there. There doesn't even have to be any ingestion. It just queries on top of that.
That makes
right?
sense. Okay, so basically I can have multiple data sources and then I can run analytics on top of it. Let's take us through what happens when I ingest data right from the API level to the storage level. Like what is exactly happening on the way?
Sure. So I think the scenario that you're interested in is, let's say I have a bunch of Parquet files in S3, right? I can query them directly, like I've just said, but I can because I can query them directly, I can also just create a table from them, right? There's this create table, my table as select star from S3 / those files. I think that's the use case you're interested in, right? So when you actually want to essentially take the data you have in S3, you want to copy it over to a local DuckDB instance, right? I think that's we can also go to a local Parquet file, what have you, of course, because we also support writing to all these different formats, right? But I think you're interested in the local DuckDB file. Okay, so what happens is we look at all those Parquet files, and we're talking about Parquet on the ingestion side. We look at the Parquet files, we basically try to check what our level of parallelism is going to be. So we check how many Parquet files are there, how big are the Parquet files, and we check how many threads do we need to run this. And usually it's going to be all the threads, but if you're working with small data sets, it's more like an optimization. If you only have a file that has 10 rows, right? You don't want to launch like 96 cores for that. Usually it's going to be all the threads, but there is this optimization. If you have very few rows, that will only use like a few threads. Then it's going to actually do the partitioning. And this is of the input data. And it does this dynamically while it's loading data. So DuckDB internally, it's a streaming engine, which means every single operator we have processes data in batches. So in Parquet as well, I think you're familiar with the Parquet format, right? In the Parquet format, data is partitioned in row groups. We check each row group is assigned to a thread, and it's done so dynamically, right? So basically the first thread that comes to the Parquet file gets the first row. The second one gets the second row group. Third one gets the third row group. And it's not done in advance. It's just done as you read, you assign row groups. You basically like greedily pick up a row group to start processing. Then the row group is streamed to the local DuckDB instance. So we basically, because it's on S3, we first download that part of the file, right? So we don't download the entire file. We download that row group, download it locally, load it into memory. Then we start streaming chunks, which is like small arrays, from the Parquet file into our storage engine, which is a columnar storage engine. And what essentially happens is our internal storage is also based on row groups. While we're loading data, initially we append to a big buffer that's uncompressed. So we just append all the data to blocks that are uncompressed, right? So if we have a bunch of integers, right, we'll just write the integers as like 4-byte integer. We'll just say 1, 2, 3, 4, 5, 6. And it's all columnar, right? So every column has its own buffer. So if you have 3 columns, you have one buffer for column 1, one buffer for column 2, one buffer for column 3, right? So I have 3 buffers that we're all writing to. And each thread has its own like local buffers because of to speed this process up, right? Like it's all parallel. When we fill one of our internal row groups with data, which is 120,000 rows, we actually compress the row group as a whole and write it out to disk. So before that point, everything happens in memory, right? So we try to, there's like some minimum amount of memory that you need. It's small, right? 120,000 rows. It's like generally a few megabytes that you keep in memory. Then the compression happens. And how the compression happens is that we essentially, DuckDB does lightweight compression. I have a blog post on this as well if you're interested in more details. But essentially, we have a number of compression algorithms that are very fast. So we have things like dictionary compression, frame of reference, delta compression. We have Gorilla as well. And we do this compression. We check for each column of that row group, what is the best compression algorithm to use for here, right? Because that depends on the data distribution, how the data is ordered, etc. Then we compress that column with the best compression algorithm, write it to disk, and then move on to the next column of the row group. And then when the row group is done, we move on to the next
So
batch.
If I understand correctly, so there is this, so I also want to understand where this 120,000 rows, the number is coming from. And so basically from the Parquet file, it takes it and appends it to the buffer in memory and then tries to compress it and then writes it to the disk in a columnar format. And I guess columnar because you want to do analytics. And I guess it also improves the compression of the data, right? You choose the best possible compression algorithm based on a specific column. Is that based on the type of the column or is it on the cardinality or?
So actually look at the data of the column. So there's basically our compression is in two phases, and both are pretty fast. And the compression is also, it's always on data that's already cached in memory. So we loop over it twice, essentially loop over the data twice. The first time we loop over the data, we check all the elements and we check, hey, is this going to compress well with delta compression? It's going to compress well with frame of reference. Is it like all the same value? Can we do constant compression? We just look at, can we do just bit packing, right? If the values are just very small. We decide what is the best compression algorithm. And then after we've decided that, we actually compress.
The ingestion part is pretty clear. So one, you use columnar data format because analytics is better, compression is better. You also analyze the data and choose the best possible compression algorithm. And then you store the data on disk in a columnar structure. And that makes sense. Typically in analytics domain, the challenging part I've seen is the updates or the mutations. Since we are compressing the data and let's say we are receiving some sort of events. So for example, talking about the email analytics, for example. So I sent an email, that email was delivered, and then I also got an event that the email was bounced because out of orderness, right? So I want to change that to, for example, it was also bounced and I want to mutate data. So how is mutation supported, or it is all append only, or how does that work?
Yes. Yeah, you can delete rows, you can update rows, and we support those in different ways, right? Because you can also update rows by doing a delete and an insert, but generally we support actual updates. Let's talk about deletions first, maybe because they're a bit simpler, and then we can talk about updates. So deletions essentially for everything works on the row group level, right? If you envision a row group, maybe just for more clarity, a row group is a horizontal slice of the table stored in columnar format, right? Think of, let's say you have a table with 1 million rows, and I have my row groups are 120K rows. So I have around 8-ish row groups, and those are then stored separately, but in columnar format, right? Everything works on the row group level. So if you want to delete a row, first you figure out to which row group does this row belong, right? And then there is a bit mask that basically contains for every row, is this row deleted, yes or no? So it's basically just flipping a bit there. There's some optimization where the bit mask isn't stored. There's no deletions, and there's like compression there as well, essentially. But that's essentially how it goes. And then when you scan, you look at that bit mask and you say, hey, this row is deleted. I'm just going to omit it when I scan, right? Like it's filtered out as you scan. There's also a compaction process that if an entire row group is deleted, we'll remove the entire row group instead of storing a deletion mask. But that's essentially how deletions work. And the bit mask is also on initially kept in memory, but on a checkpoint, it's also written to disk. So it's like persisted. Right. And when you load it, it will be there again, right? So deletions relatively straightforward in that regard. Updates are a bit more tricky, and we have some special code, actually some data types we don't support direct updates on. So DuckDB also, the type system is extremely flexible. So we don't just support like integers and strings, right? We support nested types. We support arrays, lists, structs, right? And we support those recursively. So you can have a struct within a list, or a list within a struct, or a struct within a list within a struct, right? So we support arbitrary recursion there, which means that the data types are actually also quite complex. And updates on compressed data are difficult, but updates on those like complex types are even more difficult, as you might imagine. In case you do an update on, say, a array, right? Then we do actually fall back to a deletion and insertion. So that's like our fallback case. But if you do an update on an integer or like a string, right? Like a primitive data type, like a simple data type. What we do is we have essentially a change set that kind of keeps track for every row group, right? Because everything is per row group. And then per column within that row group, what changes there are. And that's like we'll say, okay, row number 7 within row group 1, that has value 42 now because it was updated, or it's value null now because it was updated. And that again, during the scan is resolved. So it like gets merged in. And what happens during the checkpoint is that we then can actually recompress the column if there are many updates. So we can actually say, okay, instead of because you can't really change data that's already compressed. That's super difficult, right? So you need to recompress. But because it's like only at this row group granularity, even if your table is a billion rows, like you have tons of rows, you will only, if you update one row, you will only rewrite that column within that row, right?
So one thing I forgot to ask, why 120,000? And the second one about the granularity, right? So I just want to validate my understanding this. So you mentioned like everything is happening within a row group, and then within a row group, which is of 120,000 size, you have like different columns, and then whenever you make an update, you have to do it at the column level. So the granularity is the entire row group, or is it a column within that row group?
So for the updates, the granularity is a column within the row group, because deletions are for the entire row group, right? Because you delete a row. The updates, you update a column. So that's granularity is the column. And you can also rewrite only a column within a row group. That's a level of rewrite granularity. So if you have 100 columns, you update one column, you only rewrite one of the 100 columns of only that row group, right? The change sets can be quite small. Of course, it doesn't really, a row store that's not compressed still has an easier time, right? There is a cost to pay for compression in terms of mutability, because you can't do in-place updates on a compressed data store, because just by changing the value, your compression can change, right? Sometimes it's impossible, right? If you do bit packing, for example, and you have a bit packing with 8, you can only store values up to 256. Then if someone updates a value and stores like 50,000, right, or a bigger value, right? It doesn't work anymore. You need to rewrite everything because it doesn't. The compression algorithm doesn't work anymore with the data. So that's how that works, right? We have to recompress that column. Your first question was why 120,000? It's a great question. Essentially, there's a trade-off in row group size. The smaller your row groups are, the less efficient data is packed together, right? Because ideally, when you think of compression, right, you need some amount of data in order to be able to co-locate that and get the patterns, right? So if you have a row group size of, let's say, 3, compression will get you nothing, right? There's no patterns to detect and to abuse. And there's also for scan performance important, because the row groups, they are co-located physically on disk. So if your data set size is too small, you get random reads into your file, right? Like if your row groups are like 10 rows, right? Every 10 rows, you're jumping around, and that often means you lose a lot of the benefits of having a column or storage model, right? Because I don't think I mentioned this before. One of the big benefits of having a column storage model is that you only need to read specific columns, right? And that's for analytical queries super useful, because often you want to read an entire column, but only one of like 100 columns, or 5 out of 100 columns, right? So you get tons of filtering from that. But if your row groups are small, then you lose that benefit, because you do get like random access again. And in the worst case, like if your row group size is 1, then you're a row store, right? You degrade to a row store. So it's like it doesn't give you any benefit anymore. So that's the one side of why you want to increase your row group size, right? The other side is row groups are the granularity at which a lot of stuff happens, right? So row groups are the granularity of parallelism. So every thread operates on row groups, right? Their granularity for checkpointing. So if I make an update to one row and I want to like checkpoint that's this, I need to rewrite that column, right? Like that column segment, right? So the more rows are in my row group, the larger the granularity gets. So if I make my row group size infinite, like I make it like as big as possible, right? The other extreme, then whenever I make a change to a column, I need to rewrite the entire table, or like the column within the entire table. Whenever, like I also lose all parallelism, because if I have one row group, I can't parallelize over row groups anymore. You can do something with parallelizing in row groups, but with compression that gets difficult. Either way, row groups are the parallelism size. So 120K, it was chosen by us experimentally. So we checked, okay, what data set size do people have? What benefits us? Like, how does this work from like a compression perspective? And how does this work from a parallelism perspective, right? Like it's a weighted choice. And this was the number we reached that seemed to satisfy both itches, right? You can, if you have 1 million rows, which is in analytics, not that many rows, but still like a good amount, you can run it, process it with 8 threads because you have 8 row groups. But the granularity is still small enough to the point where the data of one row group easily fits in memory. You can write it very fast, read it very fast, right? So we found this to be a good trade-off, essentially.
Before we understand how the read part works, because that is like the most important thing, because after ingestion, you also want to read it in a performant manner. What happens if, so I've seen in some of the use cases, especially in analytics use case, so let's say I have to change a type of the column or something like that. How does that impact the entire workflow? Do I have to repack everything now? Or can I just take care of the new data that is coming in while the old data can still exist in the old format? And how does that work?
Yeah, so everything works on the level of the columns within the row group. And essentially what happens if you, so it's all columnar, right? So if you want to change the data type of a column, that's identical to creating a new column and removing the old column. And how that then works is that we can leave all of the other columns alone, right? We only need to concern ourselves with the one column that's removed and the one column that's changed, right? The type that's changed. So essentially what we do is we leave internally in the storage, there's like pointers to all these column segments. The old data is reused, it's not changed. The new data then gets written probably to the end of the file in that case. And then the pointers, the row groups point to that new data.
Let's talk a bit about the internal data structures that are used. At a high level, when we talk about the relational databases, they use B+ trees because they also want to have in-place updates. Some of the more write-heavy systems, they use LSM trees, for example. What is DuckDB based on?
So we use neither of those, actually. So we're very rebellious. So DuckDB is a write optimized system. It's very fast at ingesting data, but like the primary, like the way we have structured the data is around these row groups, right? So we have a bunch of row groups that are basically following each other. And then we have a one layer. You could see it as a B tree if you like squint. It's not exactly B tree. Over those row groups that allow you to jump to a different row group based on like a row identifier, essentially. So everything is ordered by a row identifier. You could see it as a B tree, but it's like a one layer B tree, right? Because we expect that the amount of row groups is generally somewhat small. And with that, because it's 120K rows per row group, right? It's a big unit. If you have 10,000 row groups, that's a lot of data. So that's like the one layer B tree. We don't really need to have concern ourselves with multiple layers. And then within there, you can do binary searches. You can do like all the stuff you can do in a normal B tree leaf as well. Yeah, I would say it's a B tree.
How are reads happening? So when I say reads, so there can be point lookups, there can be aggregation data like count or sum or something like that. And there could also be joins and on different types of tables or different data sources. To make it performant, I believe there's some indexing also happening under the hood. How does all that work? So let's start with the basic count star type of queries. How would that happen?
Sure. Like I mentioned, we do have some indexing support, but DuckDB is based around full table scans, right? It's really what it's optimized for. So like it's made like scans are fast in DuckDB. That's the use case. We do have indexes for point lookups, which is the art. It's essentially a secondary index structure that users can choose to build on top of a table. And that will then basically, the way that works is that you have a secondary index structure that contains values and row IDs, row identifiers, right? And then using those row identifiers, you can jump into this selection of row groups that I mentioned before, right? So you can say, oh, I have row ID number 200,000. Then I can look into my row groups and I can see, oh, that's the second row group. And then within that row group, you can find the actual row. We do support that. It's not our main use case, right? Like point lookups, like I said, we try to not sacrifice this use case too much in the sense that DuckDB is not terrible at the use case, but we're never going to compete with a system like SQLite that's built on the B tree, right? That's everything they do is that, right? And that's not our main use case. But we try to be reasonable at it. Our main use case are table scans. And then I'm talking about aggregations, joins, all that good stuff, right? So let's start with aggregations. So aggregations, they're relatively straightforward. You first, because it's a columnar engine, you choose which columns you want to scan, right? So you basically look at the query and you check, like the system automatically checks, oh, I need to read like column A and C, right? And we need to read two columns. Then it jumps into those row groups, and for each row group, there are the data is written in a columnar format. A thread picks up a row group, jumps to those columns, loads them into memory if they're on disk, right? So it pins them into our buffer manager. Then the data resides in memory compressed as well, by the way. Then it starts scanning from that row group. So it starts like decompressing. And that happens in small arrays. All the data is processed in chunks of 2,000 rows. So that's our batch size essentially. So we decompress 2,000 rows and then we start processing. So every thread does that by itself. Then the actual aggregation also happens in parallel. And let's just consider the simple ungrouped aggregation like accounts, right? Every thread has a thread local state that it's updating. So every thread reads a row group, right? It scans the row group, and then it will update the thread local state with its counts, right? Like how many elements it's seen that are not null. And then there's a merging phase or like a combining phase where the states of the different threads are combined together.
So you mentioned that it is optimized for full table scans, right? So let's say my query is something like select count star from some table where the created at timestamp is between this range, right? So for this type of query, like I want to filter based on this range. Don't I need any index for those, or is it all happening based on full table scan as well?
So that's actually a good point, because we do have an index for that. It's actually, I wouldn't like the reason I don't consider it an index, but some people call this an index. It's a min-max index, essentially a zone map, it's also called. And essentially every single row group has statistics on what values occur within it. And often, like when you consider like timestamps, people ingest data in order. So they will first ingest the data of the last year, of the like 1st of January, then February, then March, and April, right? It's also a natural sort of thing that as you read data you get data from a system, right? People get the data every few seconds. They get some data every day to get data. Depends on the process. It's in order generally, right? So DuckDB for every row group has statistics that say this row group contains timestamps between the 1st of January and the 7th of January. Then the next row group contains timestamps between the 7th of January and the 14th of January, right? If your data is ordered, which on timestamps it almost always is, we will prune those row groups. The threads will say, okay, I was assigned this row group, but I actually don't need to read it. So give me the next one, right? So it will very quickly skip all of the row groups and basically just go over them and only read the one that actually needs to be read.
Let's talk a bit about how the optimization for full table scan works, right? What is under the hood? What makes it super fast?
So a lot of things are inherent to a column store system, right? Essentially by utilizing both the columnar architecture plus the very efficient compression, we can scan a lot less data. So if you consider a system like, let's say I have a 100 gigabyte table, right? And I load it into Postgres. The system will create a table that's going to be roughly 100 gigabytes big, right? If I then do a full table scan, I need to read 800 gigabytes of data because it's a row store database, right? You need to read every single piece of data. Now let's take the same use case in DuckDB, right? I have a 100 gigabyte table. I load it into DuckDB. DuckDB compresses it. Let's say after compression, the dataset size can often be reduced by a factor of 3, factor of 5, right? So my 100 gigabyte data is now already smaller. It's now 20 gigabytes, right? It's like way smaller. But then comes the projection push down, right? So let's say I have 100 columns in this table and I only need to read 5 of those columns, right? Let's for like illustrative purposes consider that all columns are the same size. Every column will be 200 megabytes. I'm reading 5 columns, so I only need to read those 5 columns because the column is storage system, right? So I'm only reading 1 gigabyte of this query. So a query from which in a uncompressed row store in Postgres, you would read 100 gigabytes. In a compressed column store like DuckDB, you would only read 1 gigabyte from disk, right? So it's a factor 100. It's a giant difference. To top that off, DuckDB, of course, also buffers this data in memory. So if you're reading the same column twice, you're not even going to disk, right? It's all in memory. Then there's also the parallelism component, right? So everything is read in parallel. So this 1 gigabyte, it's partitioned over different threads, and it's all processed using a vectorized execution model, which means that the system operates on very small batches, which are cache resident. So if you do like more complex queries like aggregates with like you do some arithmetic with it or something, you do some operation like a filter, everything will be like very cache resident. Like we try to push everything as much as possible into CPU caches. If that fails, then in memory. If that fails, then of course SD or disk. But generally, you will mostly be processing data that's cache resident, and that's super fast, right?
Wouldn't it still be better to have some indexing support on top, which might still be able to reduce some of the disk scans?
So we do have indexing support, but so like I said, it depends on what your use case is, right? The problem with indexing in an analytical workload, right? So what indexes essentially allow you to do, right, is they allow you to find a specific row that matches a predicate, right? And that works really well for when you want to find one row, because you just go there, right? It's one row. However, with analytical workloads, you're often trying to find many rows, right? So, let's say that I have an index, like in Postgres, I have a B tree or whatever, right? If it's a secondary index, you find, let's say you want to read rows 1, 7, 3,000, 3,700, right? You're jumping around a lot, and you're actually reading tons of rows in the end anyway. And there is this thing that once you do random access all over the place, it may actually start being slower to use an index than not to use an index. So there's some experiments on this, and the actual number depends on how your data is organized or structured. But generally, once you read more than 2% of your table, a full table scan is faster than using an index. And in analytics, you're almost always reading more than 2% of your table. And that's when I'm talking about like a random access index, like a B tree, like an auxiliary index that allows you to jump around. The index that is super effective in analytics that we do support, right, is the zone map stuff, where you essentially can skip whole blocks of the table because it doesn't compromise on this sort of, I want to read. It's still sequential reads. You're just skipping parts of the sequential reads, right? That's still very effective. I've mentioned this before, but we do also have another index structure, which is adaptive radix tree, an ART index. And that allows you to do these kind of point queries, but we almost never really use the analytics workflows. We do use it for those point lookups, right? Because like I said, if you want to find one row, it's excellent. You don't want to scan a full table, you just want to find one row, right? So that's what we use that for.
Before I go to the MVCC part, I want to understand if there is any specific requirement when it comes to the hardware that works best with DuckDB when it comes to disk or, the number of cores, or what is the recommendation there?
So DuckDB is designed to be super portable, and we like it to run everywhere. So we don't just optimize for one specific hardware. We run like on all operating systems. We run in the browser, like I said. DuckDB works everywhere, and we try to make it work everywhere. So the single-threaded performance of DuckDB is very good compared to other single-threaded engines, but it also tries to make use of your system as much as possible. So if you have 200 cores, it will use those 200 cores. If you have tons of memory, it can cache tons of stuff, right? It supports all those things as well. So I would say if you want to speed things up, if you're doing a lot of like random accesses, like a faster disk is always going to make disk reads faster. Like it's like a fast SSD is always going to help if you read a lot of data from SSD. More RAM is always going to help if you want to cache more data, right? More cores are always going to be helpful if your data set is large and you want to process it. I would say there's not a specific setup that I would recommend, right? But it works well everywhere. But of course, if you throw more hardware at it, DuckDB will actually use it. So I think that's the system that we have tried to design, is that it scales with your hardware. A lot of people use it on their laptops, works great. A lot of people use it in the browser, works great as well. Like the WASM, the shell, like if you are interested in that at all, like I really encourage you to check it out. Like it's very fast, actually. The performance penalty is much less than you might think.
Why was ACID required for an analytics database like DuckDB?
Yeah. So I don't know if it was required actually, but maybe it's our like background as like database researchers, where we're like, obviously it has to have ACID. It's a database, right? And I think also DuckDB is used a lot with other storage formats like Parquet, right? That don't actually offer ACID, right? It's just a file on disk. It's not necessarily used, but we just thought that ACID is great to have in the sense that it allows, it gives you a lot of power. And even in analytics, it does actually give you some power, because let's say I'm bulk ingesting a file, right? Like a bunch of CSV files. I read a file, it works. I read another file, it works. I read another file, oh, there's a problem in the file, right? It's something that happens very often in data science workflows as well. DuckDB gives you the guarantee that either the file will be read or it won't be read. It's not going to corrupt your database, right? It's not going to partially read a file. You know that once a file is read, you're good, the file has been read. If the file throws an error, the database is still in a good state, right? Because it's not going to corrupt your database. You can just restart the file load of that specific file. You don't necessarily need to throw away your data, start everything all over again, right? And that for us was important. I think it's totally, a lot of other analytics systems don't support that, and it's fine. There are a lot of use cases in analytics where you don't need it. For us, it was maybe also a point of we just like ACID because, I don't know, we're database researchers, right? We're attached to that.
Extending your
like,
example,
it's
right?
flexible.
Like I process file 1, file 2, everything is good, but file 3 has a problem. And to avoid the corruption of data, I imagine you're not working or updating the same data, but you're working with a different version. And with this, I also wanted to ask you, how does MVCC work when it comes to DuckDB? And does it create like a new transaction, or what is happening under the hood to maintain the ACID property?
Sure. Yeah, so I think the MVC, like ACID, of course, encompasses a bit more than just the transaction part, the transaction isolation. So DuckDB has an MVCC model, but it doesn't actually persist anything of MVCC. So it's a bit different from a system like Postgres that writes all the stuff to disk, right? For DuckDB, all the MVCC stuff lives only in memory. And once the system shuts down, all of the transaction information, it's all lost, right? Like it doesn't actually persist anything of the transaction stuff. Only while a connection is running does it do this MVCC stuff. The way it works is that essentially you can have multiple connections to DuckDB. Even though it's an in-process database, it supports concurrent connections. They just all live in the same process as well. So it's not a socket connection, although you could then extend that with socket if you want, but it's like, we don't do that for you. You can do it yourself as the application developer. And from each of those connections, they have their own transaction context, right? And then data within DuckDB in memory has annotations that essentially version numbers, right? So every transaction has timestamps. It has a start timestamp, a commit timestamp, and data in DuckDB also has timestamps where it says this data was loaded at this by this transaction. It was committed by this transaction. We do heavy like compression there. Like every row in theory has this number, but in practice, if you do like a bulk load, it will be just one number. It will say rows like 100K to 500K have this number, right? It's not actually storing this number like 500,000 times. Because again, it's all about batch processing. Then the transactions that are reading, they will actually use this number to filter out stuff. They will say, okay, I started my transaction at time T0. This row was committed at time T1, where that's later, right? I will not read it. So I will just skip that row. And that will do it in bulk, right? So it will probably say, I will skip that row group, right? So I will skip this like bunch of rows to make it fast, right? DuckDB actually has this transaction isolation at all levels. So also at the DDL level, right? So the tables and stuff also have multiple versions. So if you create a table and then you make a change to it, right? Like you add a column, it will create a second version of the table. It won't duplicate any data. It will just duplicate the metadata, right? So like the columns, and it will say, okay, I have now a new version that has the new column. And it will like point to all of the old data for the older columns to not duplicate data.
So does every connection get like a different snapshot of data until that transaction is committed, or how does that work?
Yeah, so DuckDB supports snapshot isolation only. Like we don't support anything else, just snapshot isolation. And you always get snapshot isolation. Like we don't have an opt-out for it either. You get snapshot isolation, like it or not. And that essentially works on this principle that when a query is run, a query always has to run within a transaction. You cannot run a query without a transaction. And that determines your snapshot. So when you begin a transaction, you are assigned timestamp. That's the transaction timestamp. When you commit data, like when you write data to disk or to the file or to memory, like we also support a memory mode as well, sidetrack. When you commit data, you say this row was committed at this timestamp. Then when data is read, the transaction timestamp is used to say, do I read everything? Yes or no? Do I read this row? Yes or no? And again, like it sounds somewhat expensive when I phrase it like this, but it's all done in like giant batches, and it's all generally in the most common scenario. We check once for the row group. Do I read this row group? Yes or no? And that's it.
So in the beginning, we talked a bit about how data scientists want to process this large amounts of data, and there's problems with integration. There's a lot of friction. They don't want to use a separate database and different problems. What are other use cases DuckDB is really great for?
So I'm honestly a bit like surprised what people figure out things to use DuckDB for.
Yeah.
Like I think what makes DuckDB so great is that it's a component that you can plug anywhere, right? You can use it in your browser. You can use it as part of your Java application, as part of your Python application, as part of your Node.js application, right? Like it has bindings for all these different things. And people will just integrate it into anything that they then want, they want to analyze data into, but also just as part of data pipelines, right? Because DuckDB has this super flexible support for different data formats. Some people use DuckDB just to write a bunch of Parquet files. And because it's just the easiest way to do that, because DuckDB is so easy to use and combine with your application. So some people use DuckDB just to read a Parquet file, just to read a CSV file, just to write a Parquet file, right? Just as part of their data pipelines. I think personally, my favorite use case of DuckDB is interactive data analysis. So that's what I like to do with it. So like I love to just get a JSON file from the internet, a CSV file from the internet, whatever, just open DuckDB and just start playing around with it. So because it's so flexible, there we have a shell on like the command line clients. You can just, the syntax is really nice. I'm a bit biased there, of course, but the syntax really nice to read a file. And we've worked quite a lot on making it like a super hassle-free experience. So you can just start typing around and just write SQL against your Parquet file or CSV file or JSON file that you just downloaded, start pivoting, stuff like that, filtering, ordering, whatever, like all of the SQL goodies.
I forgot one thing which is very important to ask, and it's my bad. Where is the name DuckDB coming from?
Of course, I have the big picture. So that's actually funny. Coincidentally, I have this picture. So DuckDB, my co-founder, co-creator, Hannes, he lives on a boat because we're both live in the Netherlands, right, in Amsterdam. And there's a lot of water here, as you may be aware of. And he lives on a boat because that's what people do here. It's a strange thing. A lot of water, people live on boats. And at some point, he wanted to get a pet because pets are nice, right? And he thought, I live on a boat. What's a good pet? Ducks can swim, right? So they're awesome. So he got a pet duck. So this picture is Hannes with the duck. And DuckDB was named after this duck. So the duck's name is Wilbur. And it was just like...
Awesome.
Yeah. Ducks are great. We like ducks. So that's why.
What do you see as a vision for DuckDB that you have?
I think our vision is really world domination. It's very simple. We want everyone to use DuckDB. So I jest, of course. I think we are always like humbled by the things that people want to do with DuckDB. There's some very crazy projects out there. And I think what we want to do is just make DuckDB better at all fronts, right? Like we want to make it faster at all of those different use cases as well. We always want to improve it. We want to improve like people's experiences with like more data integrations, all that sort of stuff. And I think stability is also a big point for us. So we're still doing like preview releases. So the current DuckDB release is 0.9.1. So we haven't reached 1.0 yet. The reason for that is not necessarily that DuckDB isn't production ready. Tons of people use it in production. It's more that we're like very perfectionistic maybe, but that's still something that we are like really want to aim for, is make a product where we are like, all right, this is it. This is production ready. This is like bulletproof essentially, right? We want to achieve like that level that SQLite has, I think, achieved, where people really trust it, right? So like where people say that thing is like super robust, right? So that's what one of our main goals as well, like stability essentially.
Thanks a lot for joining and explaining us the internals of DuckDB and the use cases and how it works, and also the story behind DuckDB. So thanks a lot for joining, and I'm really excited to go back and try out all my workloads with DuckDB.
Thank you very much for the invite. It's been great.